Hello all. We'll wait for 3 to 4 minutes for the participants to come in, and then we'll start. Okay, uh, let us start the class. So, this class, we will just review what Professor Sablur has done in the lectures which we left till the last tutorials. And so in last class, I had not completed the Stokes drag part. However, that is not very, it is actually a very long calculation and a derivation to how we get to 6 pi eta v. Mm, So Stokes drag, long derivation to get to. Hmm. And before that, there were concepts of in the Navier-Stokes equation, which I mentioned last class. There's mostly stuff about momentum transfer, energy transfer, particle transfer, all these things are there. And then there's also things about conserved quantities. And also turbulence. Yes. And then we go towards quantum field theory. The uh, the video's name is also towards quantum field theory. QFT. And in this case, uh, what happens is that he talks about different Lagrangians, different Lagrangians. And what it, it describes, for example, a Lagrangian of this sort, chi, chi dot, which is ddt of chi, and chi star, chi dot star. I'll write this as an action. This function of some, it's a functional, so I should write of the. Very good. The variation of this equation, the Euler-Lagrange equation, if we compute the Euler Lagrange equation by using for example, first psi is this. It can be so there's a summation happening here. Base to So when we do this, we are going to get the Schrodinger equation. We also described how is the classical procedure, which is the Euler-Lagrange equation, giving a quantum equation. And the reasoning is that, and the argument is that uh, psi is not to be thought of as a wave function, but rather a field. So when we are when we are writing the Euler-Lagrange equation, what we are doing is we are studying the classical equations of this field, of this Lagrangian, where the fields are psi and psi star. And he also talks about different Lagrangians. There was this Ginzburg-Landau equation Lagrangian for the superconductors. There's also Gross-Pitaevsky equation, uh, which comes after this. There is also there are different Lagrangians. He also told about non-abelian gauge theories, Lagrangian, all these things like that. And then in the video, right and left movers, talk about some solutions of the Schrodinger equation. What he did is, what he did is uh, he took some kind of a Fourier transform of the field psi, and he tried to put that in the uh, he put that in the Schrodinger equation and saw what he gets. And he also found the Green's function for a free particle, which is, yeah, he also found the Green's function for a particle. Green's function, the Green's function is given by the equation. So any differential equation, D, if we have D is equal to some type of, so if we have the equation as D chi is equal to F chi, then the Green's function formalism says that I would write this as some any function J. It need not be that the I is multiplied. Then we write Green's function is given by the equation that D or G is delta x minus x naught. So and x can be a vector or whatever. And from here you solve Green's function, and main reason of why we want to solve Green's function is because if we do Green's function, uh, so from this equation over here, you can say, so this differential functions of x, Green's function is a function of x minus x naught, say. Then what's going to happen is that the x, uh, and I'm going to do an integral over x naught, g x minus x naught, chi of x naught, g of x naught is going to give you integral into x naught It's known to imply the differential operator acting on this, which will imply this. Thus, from here, we say that this is nothing but phi. Now, what we'll do is we'll find the first exercise which we are going to do is find Green's function for number one, the harmonic oscillator action. Let's do free particle first. See what happens. Let's do free particle. So, um, yeah. So there is a catch here. If I were to write the action for a free particle in one dimension, it's nothing but t half m v square, which is x dot square, which will just give me x double dot is equal to 0, which means d square dt square is equal to 0. And we need not actually we need not actually uh, worry about the Green's function here, right? Because if I were to write whatever I was saying, that integral of dt prime g of t minus t prime. Here I'm just going to put it as 0. So this part will be Dirac delta of minus t prime g of t prime, that is 0. So it doesn't. So the equation is fine, but here we have nothing to find. Let me take the harmonic oscillator as half a m omega x square. So this will give minus, and here we will run to the same problem. But now, if we have something which is say j of t times x. Okay, this is like a forced harmonic, like if we had a forced harmonic oscillator or something like that, our j of t would be something like v naught cos omega t, and we would be doing a method of such kind only. But so what I mean to say is, if we had a forced harmonic oscillator, the equation would be something like, say, suppose j of t is some j naught cos omega t, then we would find this is nothing but x double dot plus omega square x equal to j naught by m cos omega t. And the way to solve this is we assume a solution x is equal to a cos omega t, say, and we find x double dot is equal to uh, minus omega square a sin omega t, then cos omega t, then we are going to write minus omega square plus omega naught square cos omega t times a is equal to j naught by m. Now this equation is true for all t, So choose omega t as 0 and you find a to be some j naught by m times minus omega square plus omega naught square. But I want to point out that what we have written here, x is equal to a cos omega t, that is similar to saying, that is similar to this idea, is similar to the idea of Fourier transform. For example, what I mean to say is x of t can always be written as dt, integral over dt, e power I omega t, or I omega t, oh, I'm sorry, that should be d omega, and some x of omega, which I'm going to write as x tilde. If I do this, I'm going to get the same thing, minus omega square plus omega naught square, then integral e power I omega t tilde of omega is equal to j naught by m cos omega t. Is it right? Yeah. Now I'm going to say this is true for all omega t, and no, but first I have to bring it inside the integral d omega. Integral minus omega square plus omega naught square to the power omega t. Well, there is a problem. This is the correct idea. This is how to do it. We are choosing a mode of the when we Fourier transform it. But I just want to point out that this is some kind of a Fourier transform only, but we are choosing a mode. This is a way to solve, right? So whenever we have Green's function, uh, whenever we try to solve that, the first thing that we do is we go into the Fourier basis. We write the solution in terms of the Fourier modes and we try to solve them. That is what I want to point out. So if I have anything in general, then the way to solve is double dot plus is equal to j of t. Now what I'm going to do is, and x of 0 is say 0, so that 0 is say 0, for example. Now what we'll do is we'll write we'll write the different equation, which is and we'll do Fourier transform of this G and we'll write d square gt square plus omega naught square. And G is for us integral of some G omega, writing with tilde to the power I omega t equal to d omega times t. Now this operator will act inside and it will give us minus omega square plus omega naught square minus omega t minus t naught. Therefore, G tilde of omega is therefore our GT is integral of d omega e to the power I omega t minus t naught omega square minus omega square. This is G tilde omega times uh, yeah, it is just this. So there is the factor of this thing. Now we have to integrate this to get GT, or uh, So the solution of x of t will be integral over as I had written before, g of t minus t naught times g of t minus t naught times j of t naught dt. So this will be our solution. And we are going to put the boundary conditions after solving this also. So this is how to find uh, this x of t. There's other way to solve this, that is by directly doing this, and that will directly writing x of t as integral of d omega I omega t tilde of omega. So it's double that, and Fourier writing j also in the Fourier basis. What we are doing is uh, what we are doing is the same thing which we did for the Green's function, but now with x and j. We'll get minus omega square plus omega naught square integral x of t x of d omega minus omega t 0, which implies tilde omega is j tilde omega e to the power of omega t. Okay. Therefore, that t is nothing but integral of and we will have to integrate this. For this, we need to know what J is, and we'll solve this. Right, yeah, that's all there is here. Like, I hope I've cleared how to go about these problems. I don't have any specific example for it as of now. So yeah, and then after these was done, he talked about some concepts of functional integration, which is nothing but the idea of path integrals. There's nothing but path integrals. That's the so path integrals is involved here. He just involves the language of functional integrals. Like he starts with the language of the functional integrals. But if you apply it to find something like the overlap integral, you're going to get path integral. Something you're going to have fields to the power is. And all the concepts which you will learn in this chapter, the concepts of functional integral, those videos, they will be used to uh, they'll be used to study. They'll be used to solve problems and or study the path integrals more properly. Okay. And I actually intend to, instead of doing like going through this concept of functional integrals, we can also go through, like, like we can also start with directly with path integrals and see what happens there. And I think that's a better way to go about it. So yeah. May- all right. So okay, before going there, then let's take some problem and do some problem in this case only. It's from uh, from the book itself. We can do this, or we can try something else. Try, I'm just searching a problem. Yeah, let us go over through this. Better to do it that way. So let me solve. Suppose we are going to do functional integral. We are going to do it for the harmonic oscillator. The Lagrangian is half m q dot square minus half q square m omega square. Okay. And the initial conditions given to us are q of 0 is equal to qi and q of some final time t is equal to qm. You want to evaluate uh, what it's called the overlap integral between this, and this expression is given to you. For example, say this is nothing but the all the q's e to the power is of t. First, what we are going to do is we are going to find the constants of motion. That is first step. Is to know q of t, which is nothing but a cos omega t plus b sin omega t. Put the constant here, which is a, which is equal to qi, and q of t is equal to equal to qf is equal to a cos omega t b sin omega t, which implies is qf minus qi cos omega t sin omega t is equal to b. Therefore, q of t is equal to qi cos omega t plus qf minus qi cos omega t. So this is the solution with those boundary conditions. Now, we want to given this. The next thing is to evaluate the action, which is S of t. We want to find this, and this is nothing but dt e to the power dt, sorry, half and square minus. Therefore, we need to find Q dot of t, which is minus omega cos. I will take omega common. Q dot of t square minus Q of t square omega square is equal to omega square qi omega square common and qi square n square omega t plus qf minus qi plus omega t minus tqi. Minus sin q of t whole square, which is t square cos square omega t. also is like one thing. T and Q minus QI plus omega T squared plus T squared omega T. Yes, TQI QF minus QI cos omega T omega T and okay, this is it. And these terms are going to cancel. We have this term, which is nothing but QS square sin square minus cos square cos 2 omega T minus yes. Cos 2 omega T minus square cos 2 omega T QF minus Q over cos omega T plus omega T square minus QS. I'm right. Uh, there's been some mistake, I guess. Let me just explain this a little bit stupid. This person q square cosec square omega t minus q square square omega t plus minus qi over cosec omega t of omega t minus qi square. But before coming, I think there's some calculation mistake in this problem I have done. Before coming to this, why let's start with a simpler problem. And I'm so sorry, my if the answer is not matching with my notes. So I'll just do this later. Let us do a simpler problem, is uh, which is easier. We want to calculate it not for the Lagrangian this thing. Let's calculate it for the free particle with initial as some qi and final as some qi. Therefore, integral over uh, therefore the q of t is nothing but at plus b because this is a free particle, and q of 0 is d, which is qi, and q of t is uh, at plus b is qi, which implies a is equal to qf minus qi by t. Now calculate the overlap integral. We are going to have we want to calculate is equal to integral d over q e to the power I s of q t. Now s of q t will be written as integral over dt half m square, which is integral dt half m q dot of t is qf minus qi by t of m at plus d is qi. That's right. And the limits of this action are 0 to t, 0 to t. Well, this and this cancels. So this term is just QA QA. Can be made more simple, but we'll just leave it at this one. Now, what we know is, okay, there's one more thing. Yeah, let me do this as, let me not put that as 0. There will be a problem because we are going to use a property of the kernel. Oh, this T actually means, I have to repeat this again. Um, it can evaluate this without using mathematics. Hmm. There's been a slight mistake. I am going to have to, I'm not going to put that 0 because I'm going to use a property of the kernel later. All whatever we have done is correct only, but just wanted to do something else. So TA, and this is TB. Of TA plus B is equal to QI, and A of T F plus B T0 plus is equal to QF. So QI minus QF is equal to QF minus E0 is equal to A.
and P is Qi minus Qf by Tf minus T0 times T0 plus uh, Qi minus plus Qi, which implies B is equal to Qi T0 minus Qf T0 plus Qi minus Qi T0. So sorry. Qf T0 is B. Now we are going to put this in as of Q of T is equal to Q dot square is happening. This is going to be half m with the integrals. So I'm just going to evaluate Q dot T whole square is equal to Qi minus Q0 Qf minus Q0 Q T plus B Qf T0 plus Qi Tf. So we can write Qi of Tf minus T0 I'm just going to write Qi of T plus Tf minus T0 plus Qf of T0 plus Tf minus T. I'm not going to do anything like this. I'm going to call this as A with T square plus B square A square T square plus B2 A B T. Because this is A and this is B. Now I'm going to find the action. B2 square plus B2 A B T. from initial T0 to Tf, will have a T cubed by 3, a by 3, which is T cubed by 3 times T cubed, that is Tf cubed minus Ti cubed, plus B square Tf minus Ti plus AB Tf square minus Ti square. So we have we have sorry, cube of is just this. This is one. Now the the Green's function, we are actually interested in the overlap integral, but this is also called Green's function. That is, I, I'm going to write this as k of xf comma tf, xi comma ti. This has a property that, so this is A, this is B, and like this is F, which is I. This can be broken. This is still equal to F and some auxiliary P, which is between F and I, that is at some T time Tp, written as P comma I. We're going to use this property to calculate uh, whatever we get. This is the first thing which we are going to use. The second thing which we are going to use is the second thing which we are going to use is the second thing which we are going to use is the result that any AB is some normalization times e to the power e to the power e to the power uh, minus q0 e to the power classical solution e to the power by by h s of q classical. Okay. So n b to the power I h s classical is, so I'm going to drop h and I'm just going to keep I. So the path integral is has I, but we are not like we're not looking at that. And S is we have calculated S and we got S to be half m qf minus qi whole square by tf minus ti. Okay, great. Now we are going to use this is the result. This is actually this is second. So actually we have the result now that KAB is this thing and we want to put use one to know what NAB is. So NAB is just a normalization factor. Now we will do that. So KF comma I is equal to K comma K P comma P comma P comma I. So we have say yeah. So P for us is DQP. K final is NP NPI to the power IN by 2 QF minus QP whole square by QF minus TP plus QP minus QI whole square by QP minus TI. Since this is just a normalization factor, that won't come in the integral, and we are going to have to integrate this. This integral is a result. This is a result. I'm just going to write the full result for you. So basically the integral, how to do the integral is, it is simple. You just have to break the squares. You break the squares. Write it as some QP square, AQP square plus BQP plus C. Break the squares and break the squares as this, and then complete the square some qp plus alpha whole square minus some alpha square. You're going to get these kind of terms. With the square, something like this, to get a Gaussian integral. So when you are done with this, you will get that you will get uh, you will get the right hand side as nfi is equal to nf nfi to the power in by 2, since this is final minus initial, so final minus initial whole square by tf minus t is equal to n f n pi pi. The integral will give you minus 2 pi h, but h is not there. Ef minus tj, ef minus tp, tp minus ti, im ef minus ti half e to the power im by 2 ef minus qi by tf minus tm. So after doing the integral, after performing this integral, this is what you find on this side, and this side you have this. This part and this part gets cancelled, and you have NF, NFP, and the relation between these three things as this. From here, you're going to conclude something. So, trial. So the trial is NFP or anything, NAB is equal to square root n by 2 pi I times Tf minus Tp. Now, if we put this here, we are going to get m by 2 pi I. So I'll change this I above and put this minus sign. I get something like this. So m by 2 pi I 2f minus Tp, m by 2 pi, if I put this here, m by 2 pi I 2f minus Tp will cancel m and 2 pi I and Tf minus Tp. Now I'll put for this one, m by 2 pi I Tp minus Ti will cancel with this part and given another m by 2 pi I, right? And you are going to find nfi as m by 2 pi I Tf minus Tf. So by like by just looking at this, we are being able to figure out that this is the correct function. That is, NAB is equal to n
by 2 pi I d minus d. Therefore, therefore, your solution of the overlap integral of the Green's function is equal to there are factors of h cut when you include the h cut. If you include the h cut factors, this will come here and this will come here. So this is the solution. Well, take the harmonic oscillator as an homework because I think I've done some mistake in the calculation in this part. So I think I covered functional integration. Perturbation theory can be, perturbation theory. Okay. Let's do some ideas in perturbation theory. So, um, so perturbation theory and the concepts are functional integrals. So what we are going to do is that I'm going to take I'm going to take harmonic oscillator as the example itself, and uh, I'm going to show like what perturbation helps us to calculate. Okay, what it helps us to calculate. For example, in the book, if I see like perturbations, like for example, okay, this is a very good example. So for example, we have a perturbation of this one. Suppose our action is to have this one, this one, minus, minus one, which is one. Just if we want to calculate some factor f c 3 times x to the power 4. Now we want to solve we want to find the overlap integral for this or something like that. Okay. We want to find the overlap integral for this. How do we do that? Right? To do that, what we do is we say what we'll do is we'll put a new source term.
But then we make a new action. We'll not write this, rather we will put the new action. Just say g of t and x. Right. J of t and x. Now what we are going to do is this j of t is was often called generating function. So we use this. Uh, yeah, now perturbation, let me just turn to. So these are most of it are concepts in field theory, but I want you to motivate you in like QFT, in quantum mechanics, sorry. And one can do something very similar here also. Okay, we will define. Okay. Now okay. So if I have something like this, what I will try to do is square plus cx power 4. I will try to expand this series, okay? This is the way how we do perturbation series actually. E to the power I. This is some old way of doing perturbation theory. This has some name I've forgotten. 1 plus I. Somewhere there should have been a minus for this. Okay, it doesn't matter. It doesn't matter in the sense like it doesn't matter for the concept which I want to convey to you. Now we have something like this. Yeah. So this is what we have. Let me just write this. Now in the path integral, in the functional integral, what I have is so whatever quantity I am interested in. So and then look at the same thing is equal to integral of d over q d over f of t to the power I minus x of t.
Now the first this thing, the first which is multiplied with 1, this integral we know to evaluate. Well, I didn't do it here, but uh, take as of now that we know. But I didn't derive it here. I made some calculation mistake and it's kind of wrong. So yeah. And the second to see how the second term comes, to see, like, we have to calculate the integral of this stuff, right? There is an integral over dt. So, yeah. So to evaluate these kind of terms, what we will do is we will do we will put, instead of looking at this, we will see at uh, function of this kind. Here j of t is some function which you will call the source or the generating functional or whatever, like generating functional or the source. Now, one of the observations from this integral you can find is, if I do something like, suppose I write this to be, say I'm just giving some notation, z of j, and if I take functional derivative with respect to z of j, uh, what should I get? That is the question I'm interested in. Right. If I were to do a functional integral of this z of t, then what I would have to do is, in this integral z of t plus epsilon Dirac delta of t minus t prime minus s, right? Well, I'm going to just get epsilon t of t prime times x z. Well, what I should do is not this. Let me delete this. Let me write it properly. dz dj now is e power is of j, right? But I differentiated this, so I should have I del s. This is just chain rule I'm using, and this is perfectly fine. And this is going to give me nothing but an extra I. I'll put a minus I here. So this goes away, this goes away. Going to give me an x here. Okay. Now, if I do this 4 times, so minus I to the power 4, jt1, jt2, jt3, jt4, I'm going to have 4x, that is x power 4, s of j. The reason is because we're going to perform this and then you are going to get this. When you are going to perform this again, the functional derivative won't touch this. It will just touch this again. You're going to get another x, and you're going to get another x, you're going to get another. So like this, you're going to get this. Right? So this is nothing but, okay, this is still not what we want. Now you take this, you evaluate, so you take so in this page, I'm calling it number one, take one and evaluate at j equal to 0. So then you are going to get what you want. So minus I to the power 4, the derivative. So I'm going to write j1, j2, j3, j4. Evaluate at j equal to 0 will give me the second term, will give me the second term. Okay. Similarly, some other derivatives will give me third term and so on. So the third term will have something like x power 4 or x power 8, something like that. So that will be given by the third. So this is how we are going to find different terms. And we just need to know, we just need to know, we just need to know at first what this quantity is, what z of j is. We need to know. And we are done. This is not so easy every time, but for some cases it might be easy. And, um, yeah, one second. Let me actually, there are some useful things like when it can be, when it is useful, when it is not. It depends on what z of j of t is also what we are choosing. And most of the times it is very easier to do. Okay, all right. This is how we do things in perturbation theory. Now, coming to some easier. Uh, Easier. Yeah. Well, let's not do it. I think it is better when formally path integral in QFT starts. That part, whatever I was going to tell you. So, okay, this is some ideas in perturbation theory, which he said and also did some part of it also. We'll take one example and do some things. Say what is wrong with. Let me quickly do a question. So see, so we'll take a question. This is the question. So we'll take free particle and no, free particle is easy to do. This- Okay, so we have Lagrangian as okay. We already did this. Right. Now the question is find Green's function in momentum and frequency space for the particle. So the free particle Green's function which we had found was this. I'm just going to copy this. We won't put any H. Now you want to find omega t, sorry, omega k, then you're going to have to integrate over the omega and dk, and it's just the Fourier inverse. So I'm going to put e to the power I omega t and e to the power minus I omega t to the power I kx. Sorry, this goes as the other way around. So this will be plus 2 to the power I omega t minus I kx times I n by t. The, this is squared by t. And,
Mm, So the x integral seems easy. So we started that. So dt e to the power omega t square root of 1 to pi t. Complete this class. Is 50 t by a t plus 1 minus 2t by 1 plus another minus t t by n k plus 1. It multiplies by I under t under 2t. So n t by I t square by n. We put I here with a minus sign so that we do the Gaussian. There's a little thing that it's all by by n to the power minus I t square by n. And this is square root I by a. A is n and t t. This cancels with this, and we have dt power I omega minus t square by n t. Now, when we do the integral of this one, we're going to find omega minus t square by n. So, uh, so the free particle t is x is from x. So x is from minus infinity to infinity. Otherwise, we won't be able to do the Gaussian integral. T, I'm going to take some finite time so that otherwise the integral might be oscillating. So there are many ways to do this integral. One of the things
One of the ways is to, well, let's not, let's just find out 0 to 2, 2 to some, is we're going to, now, in the last 7 minutes, I just want to go over the derivation of the Green's function for a Green's function for a um, free fermion. And let us start with the Dirac equation. Sorry, the Fermi-Base equation. The one dimension. Assume E has some static potential plus some impulse, which is denoted by Dirac delta at some time and at some spatial point x. So we want to find how psi changes, psi evolves for t greater than t naught and t lesser than t naught. First, we assume that psi x of t for t less than t naught is a stationary state, and so it can be written as h cut I e n h cut t minus t naught. So it evolves at some t psi of t equal to some phi. Now for Hamiltonian, this is t less than t naught. Psi x t greater than t naught. There is no impulse, so it should again be like uh, the same this thing, right? We can use the basis states. So this for times t greater than t naught, the Hamiltonian is again static. We may write the, we may write some, this state is what do you say? The state is a linear combination of the basis states. Now integrating
Here I write this as 1 from P naught minus epsilon to P plus epsilon, P naught plus epsilon. We want to see what we get, and we are going to get the integration will only be performed here. They will firstly be performed here actually. That is I h square phi of x P naught plus epsilon minus naught minus epsilon. And in the v part, and yeah, the v part, you will have we will have this to be equal to psi is phi of psi delta x minus x naught x minus x naught, and this is psi x comma t naught because the direct delta function this part gets integrated. The other parts, this part and this part, will have when we take psi tending to epsilon tends to 0, that part will be 0. So we have not written anything there. Well, yeah, that's not entirely correct. What I wanted to say was this part will be step square to 1. So the same thing happens with this thing. Now this is like removing, so we will take epsilon tends to 0, and these parts they will go away. Okay, since this is in the integral. But we have some divergences here. We might have something here, so we are not letting them to be like letting them go away. So these two integrals, they don't contribute. It's like removing a point from a large measure zero set. So after this, we're going to put the basis states here. And T is nothing but T naught plus epsilon, that is epsilon minus minus epsilon h cut value I except t naught will be chi at t naught. It is means phi should be continuous, so phi at t naught will be just and then now since epsilon is small, this formula will nothing but we but this part only. Oh, sorry, I mean to say something else. Place expect is possible. Now, if we multiply the conjugate this thing with this, so we'll take this equation, multiply its conjugate. So one times one star implies if we do that, we'll choose something from here because shiny, and we'll also take the integrate over the states. So if we do integral over the states, we're going to have PV naught square and summation CV naught square is equal to, well, we're going to take this is it's so delta CM, so yeah, summation over V sun CV square minus delta V, and this is, well, let me do this properly. This should give us a CV to B by IH cut I star V, not by V. It's not. This comes from the Dirac delta terms. And power I plus delta of V B prime. This term comes from this part, that is this and this multiplied. So n and n prime will be written there. So this term will come from this part, and this term comes from this part. The other cross term they just cancel. Hmm. And then we can substitute this back in Shai, and then we find how it changed. All right. Now we can write this can write this in terms of the Fourier modes, and we'll find the Green's function for the free fermions. You can do that also. Okay, anyways, this much I end the class. So yeah, that's all for today.